And this situation can get even worse of reverberation and background noise. What is reverberation? It's reflection of sound against surfaces and objects, which can have a negative effect on the performance of speech communication devices. And to give you an impression, how does it like? Enough to imagine you are in a party, the voice-based assistant of your phone or of your mobile to play back music. It's a difficult task for the voice-based assistant in this situation. Also, I provide some audio samples to give this impression better. So I'm gonna play back a couple of audio samples, and the first one is in an environment with high reverberation but with low background noise. First clean speech signal of the first speaker.
New investment will be openly tendered. A contractor was due to be appointed yesterday. We are seeking a meeting with the minister.
And the clean speech signal of the second speaker.
Here he is, in effect, appointing himself a judge. Rangers didn't turn up, by the way. Please call Stella.
And the mixture or what can be captured by microphone.
New investment will be openly tendered.
Appointing himself.
A contractor was due to be appointed yesterday.
Rangers didn't turn up, by the way.
We are seeking a meeting with the minister.
Stella.
This audio sample was simulated in high reverberant acoustic condition with low background noise. Also, there is I have also another audio sample simulated in low reverberation but with high background noise. I'm not gonna play back the clean speech signal of the speaker. I just wanna play back the microphone to give the impression directly.
We are seeking the result. It was a possible upset. Other members of the family were too upset to contact. We need the chief medical officer to clarify.
So with these mixtures, that's sometimes even difficult for us to separate out the speakers and understand what they tell or say. And this brings me to our project goal, which is to develop effective source separation for realistic reverberant noisy acoustic conditions, meaning that we aim to separate sound sources while suppressing background noise and reverberation. Let's see for source separation what algorithm is being proposed so far. Actually, there are many conventional or acoustic or many conventional or classic acoustic signal processing and machine learning algorithms available for sound source separation. Typically, their performance is good, but they do not have end-to-end optimality. Why? Because the conventional methods require their parameters be estimated, like power spectrum densities, covariance matrices, and so on. And parameter estimation is done without taking into account the ultimate goal, which is source separation. They have also okay generalization, but the very good thing about this class is that they are typically interpretable. The next class is deep learning based methods, which have shown they have better performance compared to the conventional methods. And some of them do not have end-to-end optimality, and some of them actually have optimality, specifically the ones with working directly on time domain signals, as shown by the very left block diagram here. They may have good generalization to unseen conditions if a well-generalized or diverse dataset is used for training. And their interpretability is partial because of using neural network, which resists to be interpretable. And the next class is based on actually combination of DNN-based and conventional methods. But typically in a cascade way, and cascading results in non-optimality. Because of using conventional methods, their interpretability of this class is improved compared to the DNN-based methods. And there is end-to-end beamforming network. It's similar to the later method, to this combined DNN-based and conventional method. However, they are trained using end-to-end training, meaning that the gradient is passed in an end-to-end optimization way from time domain separated speech signal of the speakers to time domain microphone signals. How about their performance and their generalization? That is actually something we want to a bit explore in this talk. So in summary, the DNN-based and conventional methods are the state of art and hot topic currently. And we aim to improve the performance by end-to-end training of this class, meaning that we propose an end-to-end beamforming network. The other goal for us is to consider a large and well-generalized dataset because diversity of data defines the signal model, and therefore it's very important when deep learning comes into play. And what typically in literature is common is to train a big-sized network on a small-sized data, which may causes losing generalization. Okay, I think we have done with basically introduction, and let's go for the main part of the talk. And here is the outline. I will start by end-to-end beamforming network, which is the whole talk is about actually. And to benchmark our algorithm, we need also a Bayesian algorithm. And that's why I also talk about single channel masking-based source separation. And there we also introduce some novelties to improve the performance of the baseline algorithm. And then the third part of the talk is about combining the beamforming network and masking-based network to benefit from each other, and of course in an end-to-end way. And since data defines the signal model and therefore is very important when deep learning comes into play, I'll also talk about the data set we generated. So we will also talk about data set and the results, perhaps the least boring part, and finally we conclude. First, signal model. Assume we are in STFT domain and the acoustic field is Farfield. And we have a microphone. Here, Y denotes the stack vector of all microphone signals for the frequency index K and the frame index N. And let's drop these indices to be read easier. And the stack microphone vector can be seen as a mixture of speakers and V, which denotes noise and reverberation here. Also here, A denotes the direct relative transfer function, or DRTF, between speaker I and one of microphone. And because of Farfield assumption, the RTF can be approximated as a function of direction or theta, which is actually here. And that is why the direction of source can be approximated here using elevation and azimuth angles. Please note that here, all blocks shown in this block diagram are representation of layers of a net. And here, basically what we can see is the whole network structure of our proposed end-to-end DOA-driven beamforming network. So we start by taking multi-channel time domain mixture as input. We take STFT of these inputs, and then we extract phase or sound source presence probability, and then we use these extracted features to estimate DOA of speakers. And when we have estimated DOAs, or basically angles of speakers, then we steer to beamformer to generate STFT domain separated signals. And then we take inverse STFT to have time domain separated speech signals shown here by Z1 and Z2. As I said at the beginning, all of these block diagrams are layers of our network, and the only block diagram which has learnable parameters is this block diagram is DOA estimator. And now let's see how, let me think of it. I feel that I should say something here. And more importantly, actually, as I said at the beginning, we plan to train this whole network in an end-to-end fashion. And that is one of the novelty of this work. And now let's see how we do this. So we compute the loss based on the output or final signal, which are time domain separated signals. And it's not from an intermediate signal, something like here or, for example, here. And we take time domain separated signals, we compute their STFT, also we compute STFT of time domain targeted speakers here, and then loss here is computed. In this way, the gradient is passed in an end-to-end optimization way from time domain separated speech signal with speakers to time domain microphone signals. And in this way, even the effect of STFT and inverse STFT are taken into account in the optimization process. Okay, let's talk about the DOA estimator, which is the only block with learnable parameters. For the DOA layer, actually, we consider convolutional recurrent structure. Let's start with the input. For the input, initially we considered STFT phase features. So in a sense, no explicit feature extraction was used. But later on, and actually later on we will see, we use also SSPP or sound source presence probability. But for now, just let's assume that we use phase information as input. And the idea is to learn phase correlation of different frequency subbands to estimate DOA from different from time difference between microphones. And to do so, we use convolutional layers with small local filters. And the idea is learn phase correlation between neighboring microphones, also learn independently for each frequency subband. And basically to fulfill these two approaches, these two ideas, we just need to use a filter with a kernel size 1/2. The first dimension is related to frequency and the second one related to microphone. And this net structure is mainly motivated by the DOA estimator proposed by Sumitra. And in addition, or as a novelty or as an extension to the algorithm proposed in this work, we also use a recurrent layer basically to learn also temporal correlation or dependencies. Here is the DOA. Here is the actually more details of the DOA layer, which has a combination of convolutional and recurrent structure. So we start from phase, and then we have m-1 number of convolutional layers. M here is the number of the microphone. We have 7 microphones, therefore here we have 6 convolutional layers. And at this point, we get a vector. So it's not possible anymore to use or apply convolutional to the layer. And then afterward, we apply or we use BLSTM layer. And then fully connected layers actually come here to aggregate subband frequencies and temporal information in order to estimate elevation angles as well as azimuth angles for both speakers. On the right-hand side, we have also properties or implementation details of convolutional and BLSTM layers. If you remember, I said that we trained this DOA layer with phase information, with phase input. Alternatively, we also considered broadband sound source presence probability, or SSPP, which basically contains spatiotemporal information. They have 2 dimensions. The first dimension is direction and the other one is time. And our assumption was that because PP are more processed and they have more correlate or have more information about direction of time. Therefore, if we train the network with SSPP, it should result in a better performance. Let's see. We need to wait a bit, and we need a bit wait more to get to the results section and see actually which assumption is more correct. Okay, let me come back to this DOA layer again. So as I said here, we use a combination of convolutional and BLSTM layer. But what happens if we exclude all the convolutional layers here and we just use one recurrent layer, which is BLSTM? And this brings me actually to this slide, which is about recurrent-based DOA estimator. So here again, we have phase input and only one BLSTM layer comes into play, and the rest is actually very similar to the previous DOA layer. Also, in addition to phase, here we also try to use SSPP information as well as fusion of phase and SSPP features together to train network. Okay, so far we have talked about DOA estimator, and I think it's time to also talk about beamformer block diagram. For beamforming, we consider linearly constrained minimum variance beamformer, or LCMV beamformer. And one of the motivation to use this beamformer was that it has a closed form solution. And basically, if it could successfully place an LCMV beamformer here, then it could be replaced by any other beamformer, more advanced beamformer, or which also considered noise field adaptivity. And let's see what are the properties of this beamformer. LCMV beamformer basically aims at minimizing the power spectral density, or PSD, of the output signal while passing signals arriving from the target angle without distortion, very important. Also suppressing signals arriving from the interfering angle. And here we have the optimization problem, and to solve this optimization problem and compute the weights of beamforming, which is here shown by W, we require a direct relative transfer function, or basically DRTF of the target angle as well as the interfering angle. And as we already seen in the signal model slide, we saw that these RTFs are a function of theta, and if we know the theta, then they could be easily analytically computed. The other missing parameter for computing this beamformer is noise covariance matrix, and for that we assume the noise field is diffuse. Therefore, it's easy to compute the noise covariance matrix of a diffuse noise field. So the bottom line for this slide is that assuming we estimated DOAs of the speakers, then we could easily compute the corresponding beamforming weights for both speakers. Okay. We talked about DOA estimation, also beamforming, and the next part is how we compute loss and which metric was considered for loss to train the network. We have started from minimum square error between the target speaker and estimated speaker in STFT domain, and these variables are complex value. Also, the MSE loss function can be computed only on the magnitude part as shown here. The next one is the mean absolute error, or MAE, which can be computed as shown here, and basically this loss function motivates the sparsity and Laplacian distribution of a speech. The next one is CMSE, or the compressed version of MSE, which motivates a broadband distribution, and basically it motivates in a way in a way, it de-sparse a bit the speech signals. Also, and this loss function also can be computed using only magnitude values. And the next one is signal to distortion ratio, which is one of the most frequently used one in literature. Also, also it's possible to combine loss functions from complex numbers and magnitude numbers as shown here. So in this way, we could explore and see the importance of each part by varying alpha variable here. So if we vary this alpha and then we train a network using this loss function, then we could see and explore what is the importance of each component part here, how they are contributing to the network learning. Yeah, I think we could skip these slides due to time limitation that we have. And the next section is single channel masking based source separation, which is the baseline algorithm that we use. I should a little say something about what's the main idea about this single microphone masking based source separation. So assume we have magnitude of a reference microphone signal, one of microphones here shown by Y0, and the idea is to apply a real value gain or masks M1 and M2 to the reference microphone signal with the hope to separate speech signal corresponding to a speaker 1 and a speaker 2. So the idea is to estimate mask, and for that a network with recurrent layer have been frequently used in the literature. And here we have the structure of a recurrent masking base net, or here I call it RMnet. So R recurrent and the masking base Mnet. The input to the network is the logarithm of magnitude of SDFT of reference microphone, and then 4 BLSTM layers come in, and then fully connected layer to aggregate data or the output of the BLSTM layer from each sub-frequency band, as well as each frame or temporal information to estimate masks. Alternatively, a convolutional network can be used here, but even wanting better, what about combining recurrent and convolutional networks to benefit from each other? Because we know that a recurrent layer are good in learning memories, and convolutional network are good in extracting features, and why not to combine these two net structures together to benefit from each other? And that's actually what we propose here as an extension. I think, yeah, it's here. So a convolutional recurrent masking based net, or a CRM net. It consists of encoder and decoding layer, encoding and decoding layers, or encoder and decoder here. The encoder part basically takes the input features to higher dimensional latent space, and then we model the sequence or temporal behavior of latent features at this point via 2 BLSTM layers. And then the output sequence of the BLSTM layers is converted back up to here to the original input size by the decoder part. And then fully connected layer comes into to aggregate information together and estimate M, or masks. At this point, we are done with Mnet, and yeah, let's move to the next section. The next section is about combining the approaches we have basically talked so far. We have talked about DBNet using either recurrent or both recurrent and convolutional structure. It takes multi-channel input and and then it does beamforming to separate the speaker from each other. But typically, the beamformer outputs comes with residual noise because of the design of the beamformer we consider. For example, it doesn't adopt to noise field and also does not de-reverberation because it's not been designed for such a purpose. From the other hand, we have also talked about Mnet, which takes single channel input and does masking to separate out a speaker from mixtures. And obviously, it does not benefit from multi-channel input. Also, output signals may be distorted due to the nature of masking and suppression. And so an immediate thing comes to mind. Why not to benefit from both methods by end-to-end training? And we integrate these approaches together. First, beamforming from DB netcoms and then post-masking from Mnet. And please note here that we do this by end-to-end optimization or training. Okay, Dataset. For training, we considered speech signals provided from LibriVox. Also, there's a link here. It can be it's accessible publicly. And this data is 500 hours with 2K speakers. And for room impulse responses for the training data set, we generated or simulated 1,000 room impulse responses with different positions. And the way or technique we used to generate was image source. We basically simulated these room impulse responses for the training. Also, noise was generated by rendering to generated room impulse responses. For testing, we use data from DOPS or DIPS consisting of 5 hours data with 20 speakers. And for test data, we consider 3 measured room impulse responses with 8 positions, and then spatial noise also generated similarly to the former case that I said. And for the
can you explain a little bit generation of the spatial noise? What is your source? So single channel or?
No. So for the spatial noise, we from one hand we have a signal, a noise, a recorded noise, but it needs to be rendered toward the spatial coherence of the microphone array that we considered.
Oh, I see. So you use it a multi-channel spatial noise, which you adapted to make it what microphones are going to hear.
Exactly.
Thank you.
You're welcome. Thanks for this question. Sorry that if it was a bit vague in my explanation. Okay, and let's now move to validation data set that we considered from Edinburgh, 18 hours, 56 speakers, and then again we considered 3 measured room impulse responses, not simulated ones with 8 positions. Also, the spatial noise here is missing, but again, we consider the same strategy for generating or simulating spatial noise for validation as well. And here, basically, we could see how we could see different aspects of the room impulse responses simulator generated for training a data set. So we could see the distribution or the histogram for T60, for DRR and other parameters of or C50, which are related all to these features, these properties, these metrics are basically representative of how reverberation is challenging, or different properties of existing reverberation for the simulated data. So for example, with this T60, if it goes, for example, for normal lecture room, it is somehow between 0.2 up to 0.5 seconds. And if it goes to 1 second, it's something like that we are in a church. So it would be very reverberant. Also, we could see here the diversity of the azimuths and elevation of competing speakers we consider for this data set. The azimuths span from minus 180 degrees to 175 degrees, also elevation between minus 90 degree up to 90 degree. And more importantly, not actually more important, but another important factor is the distance, is the simulated distance between the sources to the microphones. So with these figures, I try to show the diversity of the data set that we consider to train our model with the hope to make the generalization of our network better for unseen conditions. Also for testing and validation, where we use measure Rubin pulse responses, we consider a range of T60 from 0.3 up to 1.3 seconds for, if I'm not mistaken, for validation, and from 0.4 to 0.5 for testing. And now how about how we generate noisy data? So here we have Rubin pulse responses and the speech corpus, and then we convolve basically Rubin pulse responses with the speech, and then level normalization plus scaling comes into play, as well as we consider gain from microphones. In this way, we try to augment data more and more. How about noise? How we generated noise? I think we already talked about it, as Ivan asked. And then assuming that at this point we have generated noise, and at this point we have at least a speech signal for the first speaker, we could do the same for the second speaker. So at this point we have simulated speech signal for the first speaker, simulated speech signal for the second speaker, and then we add them together. And then from the other hand, background noise would be added to basically generate mixtures. But one extra process was considered here, and it was also level normalization, also microphone level scaling to generate the final mixtures. What about microphone array setup? We use the microphone array setup used for Azure Kinect. It has 7 microphones. 6 microphones as shown here around, and 1 microphone at the center. For data setup, for training, the training data was generated in a way that the SNR follows a normal distribution with mean 8 dB and a variance of 10 dB. And the SNR was limited between -5 dB and 30 dB. Also, the angle separation between sources was randomly distributed with a maximum angle separation of 30 degrees. For testing, a similar SNR distribution was considered as for training. A bit different from training for angle separation between sources. We generated randomly distributed with a maximum angle separation of 20 degrees. Please note that here, the angle between sources here are challenging for beamformer, because when the sources are getting closer and closer to each other, it would be difficult for the beamformer to separate them out. And intentionally, we'll limit the maximum angle separation for the testing to 20 degrees to make it challenging for the beamforming, and wanted to explore the ability, the capability of the network or our proposed approach to see how it's good to do the separation task nicely. And also,
that should be minimum angle separation, right?
Really? So I did this, okay. Yeah.
That's my
So
question too.
the angles are all greater than 30 degrees. So it should be minimum separation, right?
So Sebastian, could you correct it completely? Please restate it again.
The angle is at least 30 or 20 degrees between the sources. So it's minimum.
Oh, that's true. Yeah,
right?
yeah. Sorry for this mistake. Yeah, because if I go back to the previous slide, we could see. No, actually, we could not see the distribution of the separation. Yeah, thanks for the correction. I'm sorry. Yeah. Yeah, thanks, Sebastian. Sometimes it's good that I hear some comments because I feel more interactive. I feel that I have real audience. Thanks. And all the audio samples were had sampling rate of 16 kilohertz. Okay, let's move to perhaps less boring section, which is results. For network training, we consider total number of audio sequences used for training. The total number of the audio sequences used for training was 1,000 sequences randomly selected from 5,000 sequences. And then number of the audio sequences per batch was initially to 10 sequences. We also considered 5, 15, and 20. With 15 and 20, actually the performance dropped. And for 5, sometimes we got improvement, but it was not consistent. That is why we went back to the initial setup, which was 10 sequences. And the length of each audio sequences was 10 seconds randomly selected from 30-second audio files. And the optimizer we used was ADAM and also UP training technique was used for training network. And also for STFT setup, we consider Henning window with a length of 32 milliseconds. I'm intentionally skipping these lines because I feel that I'm running out of time. Okay. And for network and the performance measure, we consider for network training as well as for evaluation. We consider BSS eval signal to distortion ratio, or SDR, which basically indicates overall errors, including interference and artifact effects. Also, we consider BSS eval signal to interference ratio, or SIR, which is maybe is a bit more related to how good signals are separated, how speakers are separated from each other. Also, we considered PESC as the other metric. Finally, results. Here, I would like to explore the impact of different loss functions for convolutional recurrent Mnet. So for the single channel masking-based network. Just to recap quickly, we have a combined loss function as we have seen it before, and there is alpha or mixing weight here. And basically here we see SDR improvement for different alpha value for different loss functions from MSE to SDR. And we see if alpha goes to 1, basically we see a consistent improvement for all almost for all loss functions. And the largest one is the one obtained or yielded by the CMSE when alpha is 1. And when alpha is 1 is basically that the loss function was computed only on the complex part. What about SIR improvement? Basically, we see the same observation in terms of that, in the sense that CMSE or compressed MSE got the best result as we see it here. And because of this, from now on, I just report the results obtained with compressed MSE with alpha equal to 1. Okay. If you still remember, for Mnet, we have one Mnet with only recurrent structure and the other one with convolutional recurrent structure, and we see here that SDR improvement and SIR improvement, as well as PESC, actually, all of these metrics are better when we use convolutional and recurrent structure together. And now for DBNet, the one that in particular we propose for an end-to-end beamforming network. So we have a DBNet with all recurrent layers, and we have DBNet with convolutional and recurrent layers. And if you still remember, for DOA estimation, I said initially that we use phase information. So here phase information is used for DOA estimation. And we see that SDR and SIR, both of them, are still positive. That's a good sign. At least these nets have not degraded source separation performance. However, they are not comparable with the results from Mnet. However, actually, these numbers are larger than the SIR achieved or obtained by recurrent Mnet, which is the most frequently used one in the literature. And basically, these numbers here suggest that there are improvement rooms to boost these numbers. And one of the immediate thing that may come to mind is that, okay, why not to, for example, replace LCM beamformer with other adaptive beamformers, and also integrate, for example, de-reverberation algorithm into them. Okay. Now, what happens if we fuse phase input with SSPP inputs, and then we do beamforming net? And we see that with this fusion, basically these numbers have not improved so much. So we got a similar performance as when using only STFD phase as input. Okay, so far from these two where Mnet basically used a single channel input, and they did masking. So they were mask-based network. And these ones use multi-channel inputs, as well as they did beamforming, DO estimation plus beamforming. How about if we combine these two together? And if we combine these two with these two, we would have 4 cases as shown here. And now let's start from this one, where all the layers are recurrent. We see that actually the SDR, all of the metrics got improved compared to these numbers. And if we consider convolutional recurrent layer instead of only using only recurrent layers, we see that SIR improvement greatly improved from 2.5 to 6.8 dB, which is, I would say, a huge improvement. And at the same time, we didn't degrade PESC. Although we have a bit drop in SDR metric. Okay. What about? I think I have not talked about these two. I was about to forget them. Okay, what about if we, for example, use convolutional recurrent for DBNet, but only using recurrent structure for Mnet, and the other way around for the next one? The results are promising, but they are not still comparable with this network. Okay, what happens if we also fuse SSPP information with phase information as we did here? For that, we consider 2 networks, this one and this one, which resulted in the best results. And then we fuse SSPP information with phase information, and then use it as input. And then we see that, for example, if we compare this line with this line, we see that we get a bit improvement in terms of SIR, but STR a bit drops. And what about this net structure, which should be actually compared with this one? We see that actually they got the same or similar STR, but SIR drops a bit, meaning that fusion didn't help or doesn't help to improve all the metrics consistently. So the best net structure resulting the best source separation performance in all considered so I want to say that among these considered a net structure, it seems that this one is the best because it results in the largest SIR improvement as well as PESC. And now let's look at the time domain waveform of this network. So at the top we have microphone signals, and then here we have separated speech signal of the first speaker, separated speech signal of the second speaker, and then we have clean speech signals of speakers. And we see that actually source separation was done in a very good way. I also have some audio samples, but not prepared actually for this presentation. It was on purpose because I felt that it may not be fair to play back audio samples every online presentation because of network artifacts. It could influence judgment. And I would like to summarize. So our motivation was to develop effective source separation for realistic reverberant noisy acoustic condition. And one of our contribution is that we develop end-to-end beamforming network with convolutional and recurrent structure. Also, we explored the influence of phase and SSPP fusion on the network performance. Also, we extended end-to-end signal channel masking based network toward convolutional and recurrent structure. And this DBNet that we developed here is a framework which can be easily extended for alternative beamforming, for example, noise field adaptive beamformer, or the beamformers also cares about the reverberation. And conclusion, incorporating convolutional and recurrent network structure improves the performance, and end-to-end integration of beamforming and deep learning improves the performance. Here are the references, and many thanks for your attention. I think also I should do it now before postponing to later, or do it after question and answer. I would like to thanks to Microsoft and Ivan Tasha for making this opportunity happen to me, that I had this opportunity to work with a great research group. Also my best thanks to my excellent mentor, Sebastian Brown. Also many thanks to Audio and Acoustics Research Group for their support, for their technical feedback, and also organizing reading and fun events. And I would like also to thank my wife. Without her, it was not possible to do this internship. And yeah, I'm looking forward to your questions.
All right, thank you, Ali.
Nice talk. Thank you, Ali. I have a single question for you.
Sure.
In several occasions, you use BLSTM.
Yes.
And they're notorious with that, the fact that they introduce latency.
True.
How much latency has your system?
Honestly, so initially, we assume that we have unlimited power of computation. So let's assume that we don't consider any limitation for that. And then I try to make a big network, a big size network, basically in a way that can be generalized enough for unseen conditions. So what I have been doing was not, for example, squeezing the network size to make it, for example, to make it functional for real-time application. So answering your question, I have not checked that. And actually for this project, we have not considered to do it.
Okay, thank you.
More questions. So I have one question on a slide you skipped a bit. So how does the network actually deal with the permutation problem between sources? So you do basically try to separate sources frame by frame, but how does the network know which to keep the source basically fixed in one output?
Yeah, that's a very good question. So that's a common problem with network or DNN-based source separation problem. So I'm trying to find the relevant slide for that. Let me bring that. I think it should be somewhere here. Yeah, it's here actually. So could you still see my slide?
Yeah, but the wrong one, I think.
The wrong one? So you don't see the end-to-end UI-driven beamforming. So you don't.
Yes.
Okay. So you ask about the permutation, right?
Yeah.
And the slide page you can see is 39 through.
No, I see 25.
Oh. I don't know how it happened. So let me unshare and then share it again. Do you see it? 39?
Yeah.
Okay, very good. So let's assume that the network does a perfect job, and down here we have separated a speed signal Z1 and Z2. So we have Z1 and Z2, and basically we don't know which output corresponds to which speakers. But just for now, let's assume that Z1 corresponds to the first speaker and Z2 corresponds to the second speaker. However, this only happens for one frame. For the next frame, if we don't constrain the network to assign the output to the same speaker as before for the previous frame, therefore the output for T2 is not, actually we have no idea about whether it's still assigned to the same speaker or not. And for that, we use R-trans permutation invariant training, which was proposed by Cole back in 2017. And the main idea is basically is that we compute loss functions. So we have two sources, and therefore we have two permutations. And then we compute loss functions for two permutations. One time between the first net output and the first speaker, and the second net output and the second speaker, and the other way around. So between the second net output and the first speaker, and so on. And then we compute this loss function and we take the minimum one. And in this way, we try to constrain network to consistently generate outputs corresponding to speakers over time, or over the whole batch. Does it make sense?
Yeah.
Ali, hi, this is Dimitra. Do you have any sense on the effect of the size of the training data on your networks?
That was huge. That was huge. So, oh, I see. Now I got your point. Yes, I have actually. So when I started working on this project and then noticed that we wanna consider a huge data set to train the network in a way to be generalized for unseen conditions. What I mean by a huge data set is something like 5,000 utterances, not utterances, 5,000 audio samples, because some of them have more than 3 or 4 utterances. When I started working on this, I was a bit afraid that, okay, if I want to train such a network, I should perhaps wait a couple of weeks to get one network to be trained well. And to overcome this issue, I started training network on something like 100 audio samples. And when I did that and then trained the network, immediately I see that the performance is not good at all. And then I moved from 100 sequences toward 1,000 sequences, and then the results got better and better. And you may ask that, how did you train on such a big data size, on such a big size data? We try to optimize the code with TensorFlow in a way that could use a GPU consistently over time. If I want to answer your question with quantified number, I'm not able, because I don't have these numbers, and basically we have not systematically explored this topic. But what I said was just my general experience with that.
Ali, so I think there's some confusion. I think it's not just 1,000 sequences you trained on, right? Maybe.
No. It's randomly selected, actually. Those thousands.
It's not only those sequences. So maybe say the amount of hours that the data had.
True. I also forgot that. Yeah. True. You're right. Yeah.
And what was that?
The number of the hours?
Yeah.
I should look at again. I don't remember any concrete number now. I
think it was around 1,000 hours.
So let me think.
The data set. But it's way more than just 1,000 sequences.
Yeah.
Right.
To say a concrete number, I'm not able to remember now, but I remember something with 1,000 hours. You're right, actually. Yeah, true. Yeah. But to say a concrete number, I should look at the data set and my code again.
I have one quick question. I'm sorry if it was somewhere in previous slides and I missed it, but did you do you have a sense for the performance of the DOA estimation on its own, and how that might affect the results, like if the beamformer is pointing the wrong way?
I think your question has 2 parts. So one question, I think your question may have 2 parts. One part is that let's say we have beamformer, and also we know a perfect DOA for that. And what happens if we steer beamformers with a perfect DOA? Actually, for training dataset, we had such an option because we simulated data, so we know the exact position of the simulated sound sources, and we did so. And numbers are even a bit lower than the numbers that we got here. It was not possible to do the same thing for test data, because test data were generated using measured room impulse responses. And with measured room impulse responses, we didn't have Oracle or perfect DOA information about them.
Mm-hmm. Okay, thanks.
Right. Any more questions? Otherwise, I would say let's thank Ali again. Yeah,
yeah, I'd like a small follow-up. So, do you think that if you train your network end to end, but if you had a place in the net, let's say the network would also estimate DOA explicitly, and you would include that as a training criterion, do you think that might help performance? I know you're saying that even with perfect DOA or with Oracle DOA, you actually got slightly worse performance, but I'm thinking if it could help maybe regularize the network somehow.
That's a good point actually to do, and I think that's one way to regularize the network better. However, at the end, when we define the loss function, the whole loss function, I assume that it would be a weighted loss function, so as a mixture or combination of loss related to source operation as well as the loss for DOA estimation. And now this question comes in how we should tune these weights. And that is actually the tricky part to do. So I think that's a good way to generalize the network better in this way. But a concrete strategy needed to be done how we should weight or emphasize the DO, the part of the loss function related to the DO estimation errors. Does it make sense?
Yeah. Thank you.
You're welcome.
Nice talk, by the way.
You're welcome. Thanks for feedback.
All right. Yeah, then thanks, Ali. It's very nice to have you. And I think with that, I'll stop the recording. We'll find out how to do that. Where can I stop this?
From the settings again, you have to go settings.